Hey, my name is Santi, and I'm one of the members of the Tensor Titans. Together, we have been working on developing a machine learning project where we identify the most socially vulnerable and communities in Virginia. So to start, we were looking through data and we were thinking, what is a project that is not only impactful, but can be applied to our lives? And we decided, okay, as third years, we've seen tragedy and the impacts it's had on the UVA community. And so we decided on using this SVI census data to determine and pinpoint these most vulnerable communities in Virginia. SVI, as of now, only uses 16 of the features of the data that it tracks. However, we want to use the 128 features and categorize them in a way that is most efficient at pinpointing this data. And so how will we do this? Using unsupervised clustering.
My name's Artie Humphreys. I'm another member of the Tensor Titans. Our first step was to clean the data, first of all. The census had a lot of incomplete data from some of the smaller counties and areas. We had to filter that data out before we could then apply unsupervised learning algorithms like k-means and dbScan to cluster the different counties and areas and communities of people.
So once we've performed this unsupervised learning by running our clustering algorithm, we must then determine a way to, assign each cluster, which represents a community, a score that represents how vulnerable they are to tragedy. And so essentially, one proposed method was PCA, Principal Component Analysis. And what this does is this reduces the number of features by combining the most heavily correlated and redundant ones into more principal components. And so by scaling this data and assigning a value between 0 and 1, we can essentially fit transform it and give it a score, again, between 0 and 1, with the scores higher to 1 being the most vulnerable ones and the scores closer to 0 being the least vulnerable ones.
Another unique sorting method that we thought we would try out is a scoring algorithm that takes the distance from all the clusters, the Euclidean distance with respect to the future space, and compares it with the worst cluster. What we mean by the worst cluster is the cluster with the lowest SVI index according to the census data. This provided a unique way of scoring that added a little more variance than our PCA scoring did during testing.
Oh, hello, my name is Hui. So I'm the third member of the Tensor Titan. So far we have our clean data. So we're gonna apply two unsupervised learning technique, which are dbScan and k-means.
Into technical details, here's a map of our geospatial data, where each point just represents a county or district in Virginia on this Virginia map. So there's around like 1,000 of them. The first algorithm we're gonna use is k-mean clustering. So this elbow plot is plotting the SSE error for finding the optimal k. This one we decided to pick k equal 21, hoping to including smaller counties where there's less like population density. This graph is about a PCA score. So we treated at PCA not just a step for a dimensionality reduction, but also an automatic vulnerability index generator for each of our cluster generated by k-means. So in this example, we can see that because the feature set included all the social vulnerability index variable plus a lot of like additional indicators like housing, demographic, and economic stress, the algorithm would just naturally amplify the difference between low risk and high risk community. We then just apply min-max normalization to cast them into a 0 to 1 range, so that a 0 mark the least vulnerable tracts and vice versa for 1. So basically what we done here with PCA is just we just convert every feature into one single feature, calling it the PCA vulnerability score, and then we scale it onto 0 and 1 and comparing it with our k-mean cluster. So this is a visualization map for k-mean clustering. We can see that's for like census tract like 904, like 501, the vulnerability is like very high, like 0.82, so we would want to look into these tracks. The same apply for like dbScan clustering, where this is like our visualization for the dbScan, and this is the score for dbScan. So why we decided to do dbScan? Because it's just give us like an additional method of trying to like check with our k-means to see if the data agrees, and also the clustering. dbScan can cluster like noise, as you see like in the last black column, and also the X mark on this graph. And comparing between dbScan and k-means, the cluster size for dbScan is for one cluster 0 is a lot of points, so that's kind of like overgeneralize everything. But typically dbScan will use like less point compared to k-means, and that leads to this standard deviation plot. So DB scan, of course, like we have like less standard deviation because they use less point, and k-means they have like higher standard deviation. So the use case for that is k-means if we want like cluster like larger region, like the whole like Virginia map, we're gonna use k-means. But for DB scan, if we want like cluster like small region like the UVA campus, we're gonna apply DB scan to have like more detailed information.
Looking ahead before we submit the final report, we really hope to tweak our k-means, our DB-scan implementations to maybe extend it to the University of Virginia community and perhaps even employ supervised learning as a mean of predicting labels for each of the communities.